Microshear planes. These fine lines are the microshear planes, and they're dipped at the same angle as these heavier macroshear planes, like the deck of cards just previously shown. Segments which do not change dip after uplift, such as segment 2, are translated upward with no apparent shearing across the bed segment. Finally, the volume of the uplifted bed is identical to the volume of the flat, non-uplifted bed. The flat, non-uplifted volume is identical to the volume of the uplifted bed. The only reference that I have found in the geologic literature that pertains to this specific uplift process is found in an article by M.S. Hubbard in the Journal of Geology, July 1996. In the article entitled "Ductile Shear as a Cause of Inverted Metamorphism, Example from Nepal Himalaya," Hubbard invokes the constant volume shearing mechanism just described to explain how metamorphic grades are structurally inverted along the main central thrust of the eastern Himalayas. Hubbard's diagram 3, or figure 3, in the text uses the same geometrical construction that I described, and in the text he refers to the deck of cards analogy. In Hubbard's opinion, this is the only mechanism that can explain both the outcrop observations as well as the fabric observations seen in thin sections. Up to this point, illustrations have been used to show how flat-lying beds are uplifted using the shear constant volume process. As a finale to this videotape, a device has been constructed which simulates how a pre-existing structure is uplifted and deformed according to the uplift process. This device demonstrates the essence of the Job 28:9 concept, namely, how folded mountains are overturned by deep crustal uplift. This particular simulation was designed to reproduce the formation of the back thrust trap discussed in the back thrust exploration model videotape. I hope you find the simulation interesting and fascinating. The back thrust exploration model details how a wrench fold is uplifted on the back side of an asymmetrical uplift to produce a low angle recumbent fold. The fold looks like a low angle back thrust on seismic data and has structural closure only on the bottom side or lower limb of the fold. To create this type of trap, we take an existing wrench fold and deform it using a device which simulates the deck of cards analogy discussed earlier. In this instance, the cards are glass plates and the pre-existing fold is reproduced on the plates prior to uplift and shearing. Let's uplift the structure now by shearing the glass plates. These structures are site-specific and that they occur on the backside of major uplifts. The structures will occur on the up-dip flank of elevated back basins. Notice how the bed thins in order to conserve rock volume. There. The uplift is complete. What started out as a steeply dipping wrench fold has been overturned by uplift into a low-angle, thrust-like structure. The structural closure now occurs on the underside of the fold, where the stratigraphic sequence has been inverted. This is the back thrust exploration model, which traps hydrocarbons migrating out of the elevated back basin behind major uplifts.